Sorry, I ran out of space on my phone, but I'm back now. So, yeah, just remember the process is called saponification or alkaline hydrolysis when we're talking about making a soap. Okay, you can't, I'll make a wee note here, you can't say hydrolysis. Okay, very important that you have to be specific. Okay. Right, so let's look at the overall process. What's happening here? So we take our fat and oil and we use our sodium hydroxide. Again, you can use potassium hydroxide, but I'm just using sodium hydroxide, and we undergo alkaline hydrolysis. Okay, and what we're going to get is we'll get glycerol, because we always get glycerol when we break down a fat and oil, but usually we get free fatty acids, but this time we're going to get free soap molecules. Okay, free soap molecules. Now, a wee note, this reaction is very economical, okay, and all we mean by the term economical is we get a lot of money, or we save money or whatever. This is very economical, as the soap molecules can be sold. Okay, because that's what we're after, we're making soap, so that can be sold. However, not only that, the glycerol can be sold. Okay, the glycerol can be sold as a byproduct. Now, the glycerol is not used in the making of soaps, okay, but if we've made glycerol, we can sell that on and get more money. Okay, so the glycerol can be sold as a byproduct and used as preparation of antifreeze. Okay, right, so that's the overall process. We're going to go into more detail. So we're going to look at the detailed process. What's exactly happening? Why are we creating soap molecules and not fatty acids? Okay, so again, we start with our fat or oil. Okay, and I'm going to draw it out. So remember, we've got the long chain fatty acid, we've got the glycerol, which is what the line sort of represents, and it looks like that. Okay, so that's our fat. We'll have an ester link here, here, and here. Okay, that's why it's a triglyceride. And we're going to combine the fat and oil with sodium hydroxide. Okay, and it's going to be times 3. We're going to use 3 of it. So that's 3 times sodium, and I'm going to draw in the ions this time. Okay, sodium hydroxide, so the sodium's got a positive charge and the hydroxide has got a negative charge. And what we're going to get, yeah, we're going to get glycerol and 3 fatty acids. 3 fatty acids. Now the glycerol I'll draw out, if you can remember what glycerol looks like. It's got 3 carbons with, so that's 2, with 3 hydroxyl groups. Okay, propan, 1, 2, 3, triol. Okay, and the fatty acid, again, it's literally just a long chained carboxylic acid, and we've got 3 of them. Now, what happens is the glycerol is sold as a byproduct. Okay, we sell it on. What we're interested in though is we're interested in the fatty acids. Okay, that's how we continue to make our soap molecules. So what we do is we take, so you could call that, I suppose, step 1. Okay, step 1's all to do with the alkaline hydrolysis of that. Now, step 2, we take our 3 fatty acids. Just going to draw it out. So we've got 3 of them, and what we do is we react that with sodium hydroxide again. Okay, and that's where the alkaline hydrolysis is coming from. Okay, so we're hydrolyzing the fat to break into glycerol and 3 fatty acids, and then we are essentially neutralizing it. We're neutralizing the fatty acids into our soap molecules. Okay, so if I draw out the NaOH, okay, again you put your charges in, and what happens, like what I showed earlier, the H of the carboxylic acid reacts with the OH of the sodium hydroxide. Okay, and what we do is we get our neutralization. We get a neutralization reaction happening, yeah, between our acid and, sorry, I should put this here, and our base. Okay, so we're reacting our base with our acid and it's neutralizing it. Okay, and remember from previously, when we neutralize, we get a salt and we get water. Okay, so what we're left with is our salt molecule, and remember we're going to get 3 of them because we've got 3 fatty acids, we'll get 3 salts. Okay, so that is our soap molecule, and because it's sodium, we call that a sodium salt. Okay, and remember we are also going to get 3 moles of water. Yeah, 3 moles of water because we're neutralizing 3 fatty acids. Okay, and you need to know that process. Okay, so it all starts with a fat and oil, yeah, and we hydrolyze it with a sodium hydroxide catalyst, and that breaks down into glycerol and 3 fatty acids. We can sell the glycerol on as a byproduct. We're interested in the fatty acids. Okay, and if I just highlight, it's the fatty acids that we are interested in, yeah, and if we take those 3 fatty acids and we neutralize them with sodium hydroxide, we're going to create this long-chained sodium salt, and that there is your soap molecule. Yeah, that's what soap is. It's a long-chain sodium salt. Right, let's make a wee note here. So, soaps are sodium salts made from fatty acids. Okay? Soaps are sodium salts of fatty acids. Now remember, a fatty acid, we've already spoke about this when we did fats and oils obviously, but fatty acids are long chained carboxylic acids. Okay, that's what a fatty acid is. Now, just as a wee side note, I have mentioned it before, but it's always nice to mention it again. We could use potassium hydroxide to form potassium salts. Okay, we could use potassium hydroxide to form potassium salts of fatty acids. Okay, that's still referred to as soaps. Okay, we're just using potassium instead of sodium. It's usually sodium that comes up. Okay, right. Now what we're going to do is we're going to look at just fix my camera. We're going to look at the structure of soaps. Okay? Right, so if we take our soap, which is our long-chained sodium salt, yeah? Now, if we look at the attraction between this negative ion and positive ion, this here is our ionic bond. Okay? Now, we can split the soap molecule up into two different parts. Okay? Now, the first part is this part. And we call that the head of the soap molecule. Okay, and this is a negative head. Okay, and it's negative because at the head of the molecule you've got a negative ion charge here. Okay, we don't include the positive sodium as part of the head. That's forming an ionic bond with this structure here. Okay, so the head is negative. Now, if we had, because it did come up in the 2019 paper, there was a positive charge here. It was a different molecule, but it was a positive charge here. This was referred to as a positive head. So just bear that in mind. Okay, and also, if that's the head, this part, okay, this part of the molecule can be referred to as the tail. Okay, so our soap molecule, we've got a head and we've got a tail. Now what's important is that you need to know the polarity of the two. Okay, and if we look at the tail, you can see there's just carbons and hydrogens. Okay, so the tail contains carbon and hydrogen only. Okay, and because carbon's got an electronegativity of carbon's got an electronegativity of 2.5, hydrogen's got an electronegativity of 2.2, the difference is 0.3, that means that the tail is going to be non-polar. Okay, so we've got a non-polar tail. The head, because we've got this negative charge here, yeah, the head, we're going to have a polar head. Okay, so the structure of the soap molecule, we've got a non-polar tail and we've got a polar head. Now I'm going to give you a wee reminder from Unit 1, from the bonding topic. Okay, so wee reminder that like dissolves like. Okay, now I'm putting that in quotation marks because we can never say that in an exam, like dissolves like, because we wouldn't get any marks for that. What we need to say, okay, so like dissolves like means that polar molecules dissolve polar molecules, and the same goes for non-polar. Okay, non-polar molecules dissolve non-polar molecules. Yeah, that's what we mean when we talk about like dissolves like. But you can't say like dissolves like, you have to say polar molecules dissolve polar molecules. And the third wee note is that you should know is water is polar. Okay, and you need to know water's polar. Yeah. First of all, it's got an electronegativity difference above 0.5, so it's got polar bonds. It's an angular shape, so it's asymmetrical, so the polarities do not cancel out. That's what makes it a polar molecule. Okay, now if we take this back to our soap, yeah, if we take this back to our soap molecule, if you remember, we've got our polar head and we have our non-polar tail. Okay, very important that you can distinguish between the two. So we've got a polar head and we've got a non-polar tail. Now, make a wee note here. So what happens is the polar head, yeah, because water is polar, the polar head can dissolve in water and maybe not, and just leave it there. So the polar head can dissolve in water, the non-polar tail can not dissolve in water. Okay, and then just make a wee side note here. I am going to go into a lot more detail in the next lesson about this, but just bear with me with this. So the non-polar tail cannot dissolve in water. It dissolves in oil, dirt, grease, etc. Yeah, and all of them are non-polar. Yeah, oil, non-polar, dirt, non-polar, grease, non-polar. And the reason it does that is because the tail is also non-polar. and non-polar dissolves non-polar. Okay? Right, last wee bit, and then we'll stop there. The non-polar tail is referred to as hydrophobic. Okay, and the polar head is referred to as hydrophilic. Okay, so these are two brand new terms that you guys are going to have to learn. Okay, so the non-polar tail is hydrophobic, and the polar head is referred to as hydrophilic. Now I'm going to break up those two words for us. Okay, so let's start with hydrophilic. Yeah, and then we'll put hydrophobic over here. Now, if we break up this word, hydro means water, okay, and philic means lakes. Yeah, hydrophobic, hydro means water, and phobic means scared of, or in this case, dislikes. Okay, so if something's hydrophilic, it means it likes water. If something's hydrophobic, it means it doesn't like water. And that should make sense to us in terms of our tail and head. So our non-polar tail is hydrophobic. It doesn't like water, and that's because non-polar molecules do not dissolve polar molecules, which water is. Yeah, but the polar head, however, is referred to hydrophilic. It likes water, okay, and that's because it's polar. Water is polar. Polar dissolves polar. Okay. Now, an example that will help you remember this, because I got taught this at school and I've never forgotten it. If we look at hydrophilic, if we look at the term paedophile, yeah, and if we break that word up, pedo means child, and phile means to like. Okay, so a paedophile is somebody that likes children. Yeah. If we look at an arachnophobe, yeah, if we break that up, arachno, we're talking about spiders, and phobe, dislikes or scared of. Okay, so an arachnophobe is somebody that dislikes spiders. Yeah, and that's how I always remember that. Hydrophilic, yeah, you like water. Hydrophobic, you dislike water. Okay, so let's recap everything we've done, because we have done quite a lot. Yeah. So we started with a wee pre-note about how the carboxylate ion is formed. Okay, so it's formed when a carboxylic acid is neutralized with a base. Okay, we get a salt. Now this is a sodium salt because we've used sodium. Yeah, and remember, in neutralization we always get salt. We always get a salt plus water. Yeah, if we had a carbonate we would get carbon dioxide, but we're not focused on that just now. Now making a soap, it's all to do with the process called saponification or alkaline hydrolysis. Do not just say hydrolysis, okay? That would be wrong. So the overall process is we take our fat and our oil, we undergo alkaline hydrolysis, and we get glycerol and free soap molecules. Remember, glycerol can be sold as a byproduct, and that's what we're after, the free soap molecules. Now, if we look into detail, what's happening there is the overall process is alkaline hydrolysis, but what we're doing is we're taking that fat and oil and we're hydrolyzing it with a sodium hydroxide catalyst to get glycerol and free fatty acids. Like I said, glycerol can be sold. We're interested in the free fatty acids. We can neutralize that with a base, yeah? And remember, when we neutralize an acid, we get a salt plus water, and that's what we get. We get a salt and we get our water. Now, our salt here is called a sodium salt because we've got sodium here, and it's a soap molecule because we've got a long chained carboxylate ion. We've got a long chained sodium salt, essentially. Okay, so remember that soaps are sodium salts made from fatty acids. Okay, because if you just use a base on a simple carboxylic acid like butanoic acid, that's not a long chained fatty carboxylic acid, it's not a fatty acid, so we don't make a soap. Okay, it has to be a sodium salt made from fatty acids. Now, the sort of last thing we spoke about is the structure of a soap. Yeah, it's split up into two parts. We've got a tail, which is non-polar because it contains only carbon and hydrogen, and we've got a polar head, okay, because it contains that carboxylate ion. Yeah, and we've got the ionic bond between the carboxylate ion and the sodium ion there. Okay, now remember about your whole like dissolves like. Yeah, so non-polar tail is going to dissolve non-polar substances like oil, dirt, grease, blah blah blah, and your polar head is going to dissolve in water. Okay, then finally, the last thing we spoke about was these two new terms, hydrophobic and hydrophilic. When we're talking about the tail, yeah, we refer to the tail as hydrophobic because it's non-polar, it doesn't like water. However, when we're referring to the head, the polar head, we call that hydrophilic because it likes water. Okay? Right, we will leave that there. Thank you.